Welcome. In this video, we're going to take a look at Newton's third law of motion, sometimes called the law of action and reaction. So the definition of Newton's third law is pretty straightforward. It says that for every force applied by one body on another, there is an equal and opposite reaction force. So in other words, if you apply a force to an object, that object will apply a force back to you that has the same magnitude but just the opposite direction of the force that you applied. And we need to note that the reaction force is going to have the same line of action as the original force, but it's going in the opposite direction. So perhaps this can be best shown with an example. So here we have a person pushing on a wall or a pillar, and so they're applying a force to that wall. So if we think about this system as from the point of view of both the person and the wall, from the point of view of the wall will see the person pushing on it, so it'll see a force in that direction. So Newton's third law says the person will see a force of exactly the same magnitude but just the opposite direction. So the person will see or feel the wall pushing back on them with the same amount of force. And both of those forces will be on exactly the same line of action. So the wall will feel a force pushing against it, and the person will feel the force of the wall pushing back on them. Here's a similar example. We've got a person doing some cross training, and they're dragging the tire around. And if we again look at it from the two different points of view, from the tire's point of view, it'll see a force pulling on it along the rope. From the person's point of view, they will feel the tire pulling back on them along the rope. The two forces will have exactly the same magnitude, just opposite directions, and they will lie on the same line of action. So Newton's third law really tells us what happens when two objects interact with each other. We'll take a look at a simple example of a book sitting on a table. So the book is not moving. That's a side view of the book sitting on a table. And we'll examine the forces acting on those two things from different points of view. So if we look at the book, we know that the book will definitely experience an external force due to gravity. And we know from Newton's first law, if that book is just standing still and it has no acceleration, that all the forces on that book need to be balanced. So obviously gravity can't be the only external force acting on that book. Otherwise the forces would not be balanced. The book would start to accelerate downwards. And so there has to be another force applied to that book. Where is that force coming from? Well, we can probably guess that the force is coming from the table. So let's first take a look at the table's point of view. So the book is sitting on the table, so the table will see the book pushing down on it. And Newton's third law says that the table will then push back up on the book with exactly the same kind of force, but with the opposite direction. So now the book has a force of gravity acting on it, pulling it down, and a force from the table pushing back up on it. And so now we have two forces acting on the book, and probably satisfies Newton's first law saying that all the forces need to be balanced. And we can apply Newton's second law to take a look at that. So we only have forces in the y direction, so we'll use Newton's second law in the y direction. And if we add up all the forces in the y direction, they should equal to the mass times the acceleration in the y direction. Since the book's not moving, there's zero acceleration. And so Newton's second law tells us that if we add up all the forces in the y direction, they should equal to zero. In other words, they should balance out. So we have the reaction force from the table pushing back up on the book, going in the positive y direction, and we have gravity acting down on the book in the negative y direction. And so we have the reaction force minus the force of gravity equals zero. And so if we do the math, we do find out that indeed the reaction force, the magnitude of the reaction force is equal to the magnitude of the force of gravity. They're just going in opposite directions. And again, it's because the gravity's pulling down on the book, so the book is pushing down on the table, so the table pushes back up on the book. That's what Newton's third law tells us happens between the table and the book. So let's take a look at a dynamic example. We have even though it may not look like that, we have a person that's getting ready to jump in the air. They're going to do a squat jump. And in order for the person to leave the ground to jump in the air, they need to be able to accelerate upwards. So they have to go from some zero type of velocity to some positive upward velocity. And if we think about how you get an upwards acceleration, Newton's second law says that you need an unbalanced external force going in the upwards direction. So you need to be able to generate an external force applied in the upward direction to the system or to the person. And so how do we get that external force? How does this person get that upwards external force? Where does that force come from? Obviously, when you're jumping, you have to push down on the ground. So when you push down on the ground, so you're applying a force down onto the ground, according to Newton's third law, will push back up on you with exactly the same amount of force as you push down on the ground. And the action of the ground pushing up on you, that's an external force acting on you, and that's the external force that you would need to generate that upwards acceleration. And so we'll call that that external force that the ground's applying to your feet as we call it the reaction force. Now, if we think about any other external forces acting on the system, of course we always have gravity. So in this case, there are two external forces acting on the person. There's the force of gravity and the reaction force from the ground pushing back up on the person because the person is pushing down on the ground. And so the goal in this case is to accelerate upwards. So we need an unbalanced external force going upwards in order to get that upward acceleration. So let's apply Newton's second law here again in the y direction. So we add up all the forces in the y direction, and that has to equal the mass times the acceleration in the y direction. So in this case, our forces are the reaction force going up and gravity force going down. And so the goal is to get a positive y acceleration, and it's the only way we can get that is if the difference between the reaction force and gravity is greater than zero. That's the only way you can have a positive upwards acceleration. If the reaction force was exactly the same as gravity, we'd be back to the book example we just looked at, and there would be no upwards acceleration. So in order to get an upwards acceleration, in other words, in order to jump into the air, the person has to have an upward reaction force that's bigger than the force of gravity coming down. And the only way that can happen is if the person pushes down on the ground such that the ground pushes back up on them with a reaction force that's greater than the force of gravity. So they need a reaction force from the ground that's bigger than the force of gravity to have an upwards acceleration. One thing to note is that sometimes it can get confusing which one of the pair of forces in Newton's third law is actually the external force in the system that you're interested in. So in that previous example, we had the person jumping, so we can see that on the left, and the person pushed down on the ground. So that was the force that they pushed down on the ground, and then the ground pushed back up on them. And so you have a pair of forces. The only one of those two forces that is the external force to that person is the force that the ground's applying to them, the red arrow. The yellow arrow is the external force that the ground would see from the person. A similar example on the right, the person running there, maybe we can imagine that the person at that moment in time is pushing down on the ground and maybe pushing backwards against the ground to try to accelerate themselves forward. And so those yellow arrows are the forces that the person's applying to the ground. Newton's third law says then that the ground will push back on that person in the equal and opposite directions, so the two red arrows. And it's those two red arrows that are the external force to the person. The two yellow arrows are what the ground sees, not what the person sees. It's important to be able to recognize which one is the external force, because we need to know the external forces in order to apply things like Newton's second law. So we're going to take a look at one more example that includes Newton's third law that helps us to kind of tie all three Newton's laws together. So here we have a person standing still and they're holding a dumbbell in one arm. And let's first take a look at what's going on between the person's hand and the dumbbell. So we'll kind of separate out. The person's still holding the dumbbell, but the diagram on the right kind of shows the two separate systems even though the person's still holding onto the dumbbell. If we think about it from the dumbbell's point of view, the dumbbell is going to feel an upward force from the person's hand. And if you think about it from the person's hand point of view, the person's hand feels a downward force from the dumbbell, because the dumbbell has the force of gravity pulling down on it. And so this is actually an example of Newton's third law, right? So the dumbbell pulls down on the hand, and the hand pulls up on the dumbbell with equal and opposite force. So we have to keep this interface in mind when we're taking a look at the rest of the example. Let's take a look at the person holding the dumbbell. So the person is still holding the dumbbell in all of these examples. But first of all, we'll take a look at it as two separate systems. First of all, we'll take a look at it as just the person. The person's still holding the dumbbell, but we're just looking at the person. And then we'll take a look at just the dumbbell and see what the external forces acting on that system is. So we're separating out, again, the person still holding the dumbbell, but we're just looking at the person as two separate systems. If we're just looking at the person, we have to think about what are the external forces acting on that person, and there's always gravity, of course, and the person's standing on the ground, so there'll be a reaction force coming up from the ground. And we know from the previous slide that at the person's hand is going to feel a downward force from the barbell. In terms of the barbell's point of view, what are the forces acting on the barbell? Well, there's gravity pulling the barbell down, and we know from that previous slide that the barbell should feel the person's hand pulling back up on it. And so those are the external forces acting on the barbell alone as it's being held by the person. Now let's combine the two things together and look at the person and barbell as a complete system altogether. And what are the external forces acting on that system? Well, there's always gravity, of course, and the person still standing on the ground, so there should still be a reaction force acting at their feet. And it turns out that that's all the forces that are acting on that system. So you might ask, what happened to the forces between the hand and the barbell? Well, there's a couple of ways to think about that, but we know from our previous discussions about forces that once the barbell was included into the system, the forces between the hand and the barbell were internal to the system, and so we couldn't classify them as external forces. But the reason why the internal forces don't matter comes from the Newton's third law. So we know that the barbell will feel an upward force from the hand, and the hand will feel a downward force from the barbell. And according to Newton's third law, those two forces are in equal and opposite directions. And so if they're both included in the system, they'll cancel each other out. And that's the reason why only external forces can cause a change in state of motion of a system, because the internal forces will always be subject to Newton's third law, and they'll always cancel out.